This is section 16.4, triple integrals, which is where the class essentially becomes completely crazy. Instead of having integrals dx dy, where you might have to switch them to being dy dx, or dr d theta, where you might care if it's dr d theta or d theta dr, now it's going to be integrals dx dy dz, where you might have to switch it to be dy dx dz, or dz dy dx, or dz dx dy, or, I mean, there's lots of choices here. Your question should be like, why? Why would you do this to me? The answer is that we will now be dealing often with functions where the input is a point in space, R3, and the output is a number. And in that case, we'll be integrating the function with respect to 3 variables, usually x, y, z, sometimes other stuff, as you'll see in later sections. So what's the goal of this section? We want to find the limits for triple integrals and actually do some triple integrals. We want to use those to find the volumes of solids, and then this thing I've hinted at where you'll have to be changing the order around is a little bit more tricky. You want to learn how to do that this section. This section is already pretty long, so I'm not going to do double integral review or whatever was planned by that picture. Instead, I'll just start by actually jumping into what triple integrals are. So let's say that you have a region, and now instead of the region being a region in the xy plane, the region is a set of points in space where the x's are between certain numbers, the y's are between certain functions of x, and the z's are between certain functions of both x and y. In that situation, the region is made up of points in space, so you can integrate over that region by using a triple integral. And you can integrate a function like the one that I have over my head here, where the inputs are points in space and the outputs are numbers. And the way that this is written out, the x's have, well, I can just write dv for now before I choose the order. But the way this is written, the x's have a range that are just numbers. So that's the outermost bounds, dx. The y's, those bounds, depend on x. And the more things that you depend on, the further into the integral you need to be. So the y's here go from g of x to h of x. That means the y integral has to be inside the x integral. And then the z's, those bounds depend on both x and y, so those have to be the innermost bounds. And that's the z integral. So your integral of f dv, you can write it once you've chosen the order as something like dz dy dx or dx dy dz. If there's no function here, then you're just finding the integral of dv, namely you're adding up all the little bits of v, so you get v, which is the volume. So we will sometimes integrate a function times dv, but if there's no function in there, it just finds the volume directly. The trickiest thing is these bounds, and as I said, the outermost bounds just have to be scalars, just numbers. And as you work your way inward, the bounds are allowed to depend on more and more of the variables. Namely, it's okay for an integral to depend on variables that are in the next integral out. And in the furthest innermost one, you can depend on all the other variables. So that's what a triple integral looks like. It has to look just completely crazy to you if you haven't done this before. Okay, so what do triple integrals do when they're the easiest form? So when there's no function in here, when you're just integrating dx or just integrating dx dy, this in one variable gave you the length of the interval. Because you would integrate this and you'd get just x, and it would go from b to a. So you'd just get b minus a. And that's how long the interval is. This is the double integral of dA, so you're adding up all the little bits of area. This is the area of the region. And then this, even though it looks insane, if these are all numbers, then you're integrating dV for like a rectangular box, and you get the volume of the box. So it's just the integral of a little bit of arc length is the arc length. This is length. The integral of a little bit of area is the area. Then the integral of a little bit of volume is the volume. So this is our attempt at a slicing picture. I've showed you a bunch of different slicing pictures where you would, like, in Calc 1 or Calc 2, you'd slice up the interval that you were integrating over into little pieces. This is called partitioning the interval. And those little pieces were the dx. Earlier in this chapter, we were slicing up the base of a region into like a grid, and those grid bits were dx dy, and that was dA equals dx dy. Here, I'm slicing in all three directions and getting a bunch of little boxes of all different sizes. And I would say that this way is in the y direction. So it's a little bit of y. This one's coming out in the x direction, so this is dx. And this one is going in the z direction, so this is dz. This is kind of like the geometric argument that dv can be written as the product of dx, dy, and dz. In any order. But the order you pick will affect the like integration bounds. You might imagine that there are other ways to slice up space. Can you imagine this? I guess we'll put that off mostly until a later section. Yeah, let's just not think about it for now. But for now, imagine that you could slice all of space up into little tiny boxes by slicing this way, and slicing this way, and then slicing horizontally. And you'd get lots of little tiny boxes, and they'd be little bits of volume. Yeah, I'm not doing anything with that. Okay, so let's just see one in action where we use a triple integral to just try to get the volume of a sphere. So here's my plan. A sphere is very symmetrical, so I'll just do like the front top corner of the sphere. We'll find the volume of 1/8 of a sphere. I don't know, I'll call it V8. Just so that I don't have to deal with anything too crazy. We're having a sphere of radius A. So its base in the xy plane is a quarter of a circle of radius A. And then its coordinate traces are all quarter circles. And you can kind of like, I'm just doing the front corner of the sphere here. So V8 will be this volume. Then at the end, I'll multiply it by 8. Or actually, what's really going to happen is at the end, I'll be off by 8 and I'll be confused, and then I'll remember. So, how do I find V8? Well, I need to take a triple integral of dv. So I'll slice this, I don't know what shape it is, this 1/8 of a sphere up into little tiny pieces and add them all up. This region is the region V8. Okay, so to do this, I need to find the bounds for x, y, and z. Okay, let's just pick an order for now. If it turns out that things get too hard, then we'll do it in a different order. But kind of like I think the easiest base order to do this in, like the way that you've been trained to think about the variables, is probably this way. So first let's get the x bounds. The x bounds are just on numbers because they're the outermost integral. So x, the lowest x is x equals 0, and the highest x is x equals a. No problem. Then I need the y bounds. The middle bounds are the trickiest, but the way that you can find those middle bounds is just draw what happens when you look down on the shape and see what it looks like in the xy plane. Because the y bounds need to be a function of x. So here's what the region looks like in the xy plane. This function is y equals square root of a squared minus x squared. It's the top of a circle. So the bottom function is y equals 0, and the top function is this function of x. Looks like I didn't leave enough space for z here. Finally, we need the z bounds. The lowest z is z equals 0 at the base here on the xy plane. And the highest z is, oh my gosh, well, it's whatever the equation of a sphere is. And the equation of a sphere is x squared plus y squared plus z squared equals a squared. So if I solve that for z, that'll be the top of the sphere. So let's just stop for a minute to make sure that these bounds make sense and like line them up with what we did on the first page. So on the first page, I claimed that your outer bounds were just going to be numbers. Your inner bounds would possibly depend on the outer variable. And then the furthest most inward bounds could depend on all the other variables. And that's what we got here too. The outer bounds were numbers. The next one in depended on x. And the next one in from there depended on x and y. The middle bounds are just the trickiest because it's like, what do I even do? But if you can say, oh, when I'm looking at the middle bounds, I'm looking at x and y, then you're good. Okay, so now I could do this integral, but I think you should remember back, was it just the last section that was polar coordinates? That this shape is circular. And so what am I doing here? Like, I shouldn't really be doing this like in rectangular coordinates. I know that dy dx equals r dr d theta. Pff, not r dr theta. If I do this more carefully. And if I do it this way, then I might be able to escape some of the painful stuff of this integral. So let's do it that way instead. Wow, I really did not leave very much space in these notes for this problem. So if I decide to switch x and y into r and theta, the z bounds will stay the same, except x squared plus y squared is r squared. dy and dx will be r dr d theta. And then I just need theta bounds and r bounds. Well, the theta bounds are from 0 to pi over 2. And the r bounds go from 0 out to a. This is so much better. The integral is so much easier. So let's do it this way. I don't know, the fact that it's a triple integral, somehow it doesn't really matter how many integrals there are. What matters is, can you do enough changes of variables to make the integral less painful? So let's do this integral. The outer integrals are just sitting here waiting for us. Those are the dr and d theta integrals. The inner integral is just z from 0 to this crazy bound. So that's just the crazy bound. And now I'm down to 2 integrals. Then I do the innermost integral, the r integral. So I started by doing the z integral, and then I'll do the r integral. The r integral looks like it's set up so that I can do a u substitution. So I'll let u be a squared minus r squared. du is minus 2r dr, which is good. I have an r dr. And yeah, it's probably really good to change the bounds here. So I had r was going from 0 to a. Now I'll have u going from, well, I'll plug in r equals 0, u is a squared. And when r is a, u is 0. So my outermost integral is just sitting here waiting for me patiently. The inner integral is now minus a half square root of u du. And the bounds are a squared to 0. I feel like I've done this integral before, like last section. I don't know. Okay, there's no thetas in the outside integral, so the outside integral is just going to multiply the result by pi over 2. The inside integral, I'm going to switch the order of the bounds, whatever, I'll just deal with it. So we'll just do the power rule. Multiply by 2/3 and make the power 1 bigger from a squared to 0. Plug in 0, get nothing. Plug in a squared, and I'll get a squared to the 3 halves. Oh dear. Okay, so a squared to the 3/2 is a cubed. And then I have pi over 2 times a third is pi over 6. I feel like I skipped so many steps that I have no chance that this is right, but let's just see how we did. So this is my volume of 1/8 of the sphere. So my final answer for the volume of a sphere is I multiply this by 8. So I have 8 pi over 6 a cubed, and that simplifies to 4/3 pi a cubed. And that is right. That's the right volume. Okay, so what are you supposed to take away from this? First of all, that like, yes, this is crazy and you should feel really powerful when you're doing it. I don't want you to, I don't want you to be afraid of what you're doing, but I do want you to be impressed by what you're doing. Next is, how do you deal with the bounds? The outermost bounds are just numbers, like before, and that as you go further in, you can have functions in the bounds, as before. But it's more precise now with triple integrals, where the middle bounds can depend on the outermost variable. The innermost bounds can depend on all the other variables. Then, anytime you see a disastrous integral coming at you, you should imagine, this is the thinking outside the box pun, think outside the rectangular integrals, and imagine doing it in polar coordinates instead, and your life is probably better. Yeah. I like this problem. I don't know. It seems good. Okay. Let's do another one. We're going to try to find a volume. So I already know what the plan is. The plan is that the volume is the triple integral of a little bit of volume over some region. And then I will try to get this solid, whatever is being described here, get all of that information into the bounds. So let's try to do it. I'm going to have z equals the square root of 1 minus x squared. What is that? Well, that's the top half of a circle, but it's a cylinder, and you can tell because the y's are not mentioned. This was all the way back in section 13.6, so hopefully it doesn't feel like 100 years ago. But if y does not appear in the equation, then y can be anything. So here's like x, y, z. Z is square root of 1 minus x squared. But then y can be anything. Let's get another color. So you get a cylinder with these rulings. So this is z equals square root of 1 minus x squared. The xz plane, okay, well the xz plane is just the place where y equals 0. So since we're bounded by the xz plane, I guess I can get rid of this part over here. The xy plane, okay, so we won't go below the xy plane, and then y equals x. Oh dear, y equals x. Okay, y equals x comes out here in the xy plane, but z can be anything, so it's a plane that slices through this, I don't know, loaf. I can kind of imagine it, but my drawing is terrible. Like you have a loaf of nice green screen situation there with my hands. Okay, you have a loaf of bread that for some reason is just like half circle shaped, and then instead of slicing it like a normal person, instead you like slice it at a diagonal, and you see what kind of shape you get. Am I gonna be able to draw it? I don't think so. Okay, but I have enough understanding of what's going on that I will be able to get the bounds for the integral, even though I can't get a great picture of it. So I'm going to do the same usual like order that I usually do, where I'll try to do dz, dy, dx, and this is just my default order. I'll switch it around if needed. So the x bounds, well, I can see that the lowest x is 0 and the highest x is 1. So that I can get from the picture. Then the y bounds, this is where I really recommend that you go look at what's going on in the xy plane. In the xy plane, we have this y equals x as the main divider. And then what does this thing do? Well, it goes out to x equals 1 in the xy plane. Notice that even though this is a curvy shape, this thing I've been referring to as like a loaf of bread, even though it's a curvy shape, in the xy plane it looks just like the line x equals 1. So the region in the xy plane is this triangle. To describe this triangle using bounds, we say x goes from 0 to 1, and y, the bottom y is y equals 0, and the top y is y equals x. Then the z bounds, well, what's the lowest z? The lowest z on the floor here is the xy plane, which is z equals 0, and the highest z is square root of 1 minus x squared. So now the question I think you should ask is like, does this integral look good? Or would it be better if it was done in polar coordinates or something like that? I don't like the square root of 1 minus x squared. It's like pretty bad. Okay, my instinct here is that I don't want to switch to polar coordinates because the base region here is a triangle. And if you try to write a triangle in polar coordinates, it gets a little bit sketchy. Like you can do it, because the angle goes from 0 to pi over 4, and the problem will be trying to write a horizontal line or a vertical line in polar coordinates. You can do it, it'll have like a secant theta in it, so it's the question of whether like secant and cosecant is worse or whether this is worse. The reason so the triangle makes me think I should stay in rectangular coordinates, but I know that the first thing I'm going to do here is take this integral, and then there's going to be a square root of 1 minus x squared, so I might end up having to do a trig substitution. That's the reason to leave rectangular coordinates and go to polar coordinates. I have like a reason in both directions, so what I'll do is I'll just try what I have written here, and if I ever get stuck with an integral that I don't like, I can just switch it around and try something else. So let's just go and see what happens. So this integral, the inner one, is the integral of dz. So it's like the integral of 1. So the outermost integrals are just going to sit here and wait. The integral of dz is z, and the bounds are from 0 to root 1 minus x squared. Okay. I can plug in those bounds, and I'll be ready to go for my second integral. This is what I was worried about, was the integral of square root of 1 minus x squared. But notice that the next integral we get to do is a y integral. So this is the integral of a constant. So this worked out just great. I'm glad I didn't abandon it and go to polar coordinates. This constant can pull out of the y integral entirely. And then I can do this y integral from 0 to x. That result is x. Now we do finally have to reckon with this square root of 1 minus x squared, but I have my x here to help me out, so everything's fine. So I'll do a substitution. I'll let u be 1 minus x squared. And I feel like I've done this substitution in every integral for the last, like, 3 hours of recording these videos. I don't know what's going on here, but I can solve for x dx. X dx is minus a half du. I've got some bounds here that are x bounds. X goes from 0 to 1, so I'll figure out what happens with u. When x is 0, u is 1. When x is 1, u is 0. So the integral is now from 1 to 0. I have a minus a half and a du, and a square root of u. Okay, integral of square root of u is 2/3 u to the 3/2, so this happens again. plug in 0, plug in 1, and I get plus a third times 1. So it is a third. So it's 0 minus a third. That is a third. Huh, cool. So this region, it's like a pretty complicated region, and it's hard to even draw it. But when you draw it, you get enough information to get the bounds down, and that's what you're really aiming at. So it's about, like, we had a section 13.6 at the very end of like 2 chapters ago where we were trying to draw 3D shapes, and it was kind of funny because like it's hard to draw them. But it's all about what the goal is. The goal is not to get a perfectly pretty artistic picture of it. It's to get enough of a useful picture that we can do the calculus that we need to do. The main tactic that I used here is when I was doing the middle bounds, when I was trying to figure out what to use for the y bounds in the middle, I drew the result, like the shape, what it looked like in the xy plane. And that is what allowed me to find the y bounds. So, triple integrals are sweet. I don't know. I don't know that I'm going to convince you of that, but this is awesome. So, this is a really important word, especially for quizzes and exams. If someone tells you to set up an integral, please remember to not do the integral. It means that they've found a problem for you to do, and they don't want you to do the end of it, because the end of it is a complete mess. So we're just going to set up the integral. It's going to be a volume, so my plan is that the volume is the integral over the region of a little bit of volume. It's going to be a solid that's bounded above by a paraboloid and bounded below by some plane that's at some weird angle. Okay, so let's try to figure out what to do here. I think the z bounds are going to be on the inside because I have z as a function of x and y. So I think my base plan of just like always defaulting to dz, dy, dx is working out again. The bottom plane is z equals 1 minus y, and the top plane is 1 minus x squared minus y squared. Now the question is, what are the other bounds? Like, what's the lowest x, and what's the highest x? Okay, well, here's the paraboloid. Z equals 1 minus x squared minus y squared. On the xy plane, it is a circle of radius 1. So let's get the axes here. Then the plane z equals 1 minus y. Well, the plane z equals 1 minus y is a cylinder. And what I mean by that is that there's a variable missing. So x can be anything. So I'll first draw it in the section where x equals 0. That's in the yz plane. When x equals 0, z equals 1 minus y just connects these points with a straight line. Then x can be anything, so I repeat that straight line at every value of x. And it's going to like come through this and like slice off a piece of the paraboloid. Oops. Lines parallel to x should stay parallel to x. So I'll head off in the x direction. So I'm slicing through this paraboloid at this like weird angle, at this 45-degree angle. Okay, well, again, the goal is not to get a perfectly pretty artistic picture. It's to get enough information that I can figure out what the bounds are. So what's the lowest x and the highest x? That's actually difficult, because I don't think x is going to make it all the way out to x equals 1, due to how this like slices. So I guess I'm going to have to draw the xy plane. And figure out, like, how does the plane actually intersect with the paraboloid? Like, can we solve both z equals this and this at the same time? So that would be 1 minus x squared minus y squared equals 1 minus y. I think we can solve this. Like, I could solve it for x. So I'll get everything over to the left side. The 1's cancel. So I'll have y minus y squared is x squared. Wait, x and y are both squared, so that's not a good plan. I don't want to get I don't want to get like the x's on one side and the y's on another. Oh, canceling the ones is still good. Because the x and the y are both squared, this is going to be like a circle or an ellipse. So I'll get the x's and y's over so that x squared and y squared are both positive. And then I'll complete the square so that I can see where this circle is. Y squared minus y, to make it a perfect square, I would need a fourth here. If you need a refresher on completing the square, it's totally fine. You can ask me in an office hour or ask your instructor in an office hour. Like, we have to teach completing the square in every class because no one ever takes it seriously. But that's fine, it's nothing against you. So to make this a perfect square, we need to add a fourth. I can't just randomly add a fourth to the right side, so I'll also add a fourth to the left side. Then when I factor this, I'll have a fourth is x squared plus y minus a half squared. So what is this shape? This shape is a circle centered at 0, a half, with radius a half. So this intersection between the plane and the paraboloid is this circle. Nice circle. This circle. Right there. So now we can actually see from this algebra we did what the like cross section is of the region. The lowest x is minus a half, and the highest x is plus a half. Similarly, the lowest y. Okay, well, the y is now going to have to be a function of x, right? We're going to need to find, here's the low y and here's the upper y. So I need to solve for y in terms of x. So y minus a half squared is a fourth minus x squared. Square root both sides. And y is a half plus or minus square root of a fourth minus x squared. The minus term will be the bottom one. Oh yeah, this totally leaves enough space. And the plus will be the top bound. So the key thing here, as in the previous problem, was when you're stuck, try to find what's going on in the xy plane. The xy plane, like the projection down to the xy plane, will always be needed to get the middle bound, but sometimes it helps you get the outer bound as well. Here it told us that the x's go from minus a half to a half. So if we look down on this region from above, it's gonna look like a circle. This is complicated enough that let's get a picture of it from a computer program that can draw in 3 dimensions. Since we're trying to draw in 3 dimensions, I'll go to geogebra.org/3D. So we've got z is 1 minus x squared minus y squared, and z equals 1 minus y. So here's my slice that I was trying to draw. It's actually like not terrible. But then what I figured out from algebra is that if you look down on it from above, you get a circle. Oh wait, xy plane, x would go that way. If you look down on it from above, you get a circle of radius a half, this circle. That goes all the way from y equals 0 to y equals 1. Now the actual shape that we're looking at is some like sliced off little piece of the paraboloid. But looking at its x and y bounds, you get a circle that, like the circle that we found the equation for. So, nifty. Seems good. Okay, let's do a couple more. Oh, remember that this was just set up the integral. If I was actually going to do this integral, I would definitely switch it to polar coordinates, because check out this circle. And then you would have to remember how to write an equation of a circle that looks like this. This circle is, I think it's r equals sine theta. But you would go to Desmos to figure out, to make sure that you had the right one. Let's just make sure that I have it right here. R equals sine theta. Yeah. But what level of expertise in polar coordinates are we expecting in this class? I don't know. Maybe we should expect more, but we don't. So we just tell you to set up this integral. Okay, consider this integral. It gives you an integral, and then it tells you, hey, how about you try switching the order around? The skill of switching the order of the integrals is really important because you need a way out anytime an integral ends up impossible. So let's just practice it. This one is to switch the, well, first it says to sketch the region. So let's do that. I recommend you first draw what's going on in the xy plane, or whatever is the last two variables. So here the last two variables are x and y, so we should look at the xy plane. This says x goes from 0 to 1. Oops, let's make 1 a little smaller. And y goes from -2 to 2. Notice that the y's don't depend on the x's, so that means the base of whatever this region is in the xy plane is a rectangle, a 1/2 rectangle. Then z goes from 0 to square root of 4 minus x squared, 4 minus y squared. So when we go into space, y is going to be negative sometimes, so let's move over. Having trouble with straight lines. So the base goes from, x goes from 0 to 1, and y goes from -2 to 2. But z is, the top bound is z equals square root of 4 minus y squared, which is a circle of radius 2. Now, z equals square root of 4 minus x squared does not have, I keep saying x, which ruins everything. Z equals square root of 4 minus y squared does not have x in it. So this circle is repeated for every x. So like over out here at x equals 1, it's also a circle of radius 2. So the region is looking like this. Don't know why this is dotted. It's kind of nice. It's like half of a cylinder. But technically it is a cylinder. Whatever. Okay, so this is the integration region. Goes out to 2 and -2, and x is 1, goes up to z equals 2. Now this question says, try dy dz dx. Okay, well, you want to try to get the same picture, but the base you're considering is the xz plane, because x and z are the last two. So let's just look at what happens in the xz plane first. In the xz plane, it looks like we're looking at a rectangle. Like if you sliced through this, like it was a cake or something. I guess I'm hungry. Slice through it like a cake, you'd get a rectangular slice. The z goes up to 2. And the x only goes out to 1. So this is what's going on in the xz plane. That means that the bounds for x and z will be x goes from 0 to 1. X is the outermost variable, so I do its bounds on the outside. The z's don't depend on x. Z goes from 0 to 2, no matter what the x's are. Notice that I got a little bit like worried there because wait, out here z does not go up to 2, but that's not the point. The point is in the xz plane, what does it look like? And the z's go from 0 to 2. Then all the complicated stuff will happen in the y's. So given a specific x and z, what do the y's do? So you like pick a point in here. What's the range of y's? The lowest y is down here, which is somewhere on this like circle, and the highest y is over here, which is somewhere on this circle. So this side is the bottom y bound, and this side is the top y bound. Okay, what is that? Well, that's this circle, z equals square root of 4 minus y squared. So the y bounds will be, solve this for y. Y is plus or minus square root 4 minus z squared. Notice that this plus or minus has come up twice, that like when you square root both sides of an equation, you need the plus and the minus. Here's the minus side over here. These are the y's that are negative, and here's the plus side over here. These are the y's that are positive. So the y bounds are from minus root 4 minus z squared to plus root 4 minus z squared. And this is the same volume. It's the same region, just written in a different order. So this, I think, can be really scary. And even I actually got a little unnerved for a moment there where I was like, what? Like, z just goes from 0 to 2? No, it doesn't. But that's why we have these, like, plans to help us feel like we're organized when we're going through something unfamiliar. So you look at the last two variables, look at the projection of your shape down onto just those two variables and draw that first. Then you'll get these two bounds done. Then you'll be able to like see what happens to the last variable, and it can depend on whatever it needs to depend on. But getting these middle bounds correct, I think, is critical, and then you'll be fine. Let's make sure that everything looks fine there. Yeah, it looks fine. So at the very end of this section, we will use triple integrals to find average value. The average value formulas have been the same over and over and over and throughout calculus, which is if you want to find the average value of a function, you should integrate the function over the region. This time, the function is a function of 3 variables, so we're doing a triple integral. And then divide by how big the region is. I don't know, I guess volume of D. The average value formula in Calculus 1 was 1 over the size of the interval times the single integral of the function. Earlier, when we had double integrals, it was 1 over the area of the region times the double integral. And now it's 1 over the volume of the region times the triple integral. So it's the same formula over and over, and yeah. That's not a very convincing reason. I guess the issue is that, like, say the function gives you the temperature. So the function is in degrees Celsius, and the volume is measured in meters. No, the volume would be measured in cubic meters. So you've got like a room, and it's a different temperature at every point in the room. So you integrate the temperature over the whole room to try to figure out like how much temperature there is going on. The problem is that the end result that you get is in the units of degrees Celsius times cubic meters. And that answer, that integral, it does take into account all the temperatures throughout the room, but it's in weird units that don't mean anything. So that's how you can remember that you need to do this, because like the average temperature of the room, you need to cancel the cubic meters somehow. And so like just divide by the volume of the room and you've got it. We know from physics that like you can't derive every formula by just getting the units right, but like getting the units right is an easy way to tell if your formula is wrong. So if you're trying to find an average value and you just remember like, oh, well, it's an integral, you should check the units and see that the units are wrong. So you've missed a term that is meters cubed, and that can help you remember what you've missed. So let's do an example. Hopefully it's a temperature example. Yes, it is. So I've got a 1 by 1 by 1 cube, 1 centimeter, little tiny cube. Its temperature is different at every point in the cube. Depends on where you're looking. You plug in an x, a y, and a z. That's this kind of function that I have up above me. You plug in an x, a y, and a z, and it gives you a temperature. So at like the upper corner, 1, 1, 1, the temperature is 29 degrees Celsius. In the bottom corner, 0, 0, 0, it's 20 degrees Celsius. So the temperature is varying throughout the cube continuously. We want to know the average temperature of the cube. No problem. The average temperature of the cube is the average of this function. The function is called t. It's 1 over the volume of the cube, which is, it's 1 by 1 by 1, times the triple integral of this function. dv over the cube. Now, this thing is in degrees Celsius, and this dv is in cubic centimeters. So the cubic centimeters from dv are going to cancel with these cubic centimeters, and I'll get the degrees Celsius that I want. Now I need to figure out how to make the region show up, like with bounds. But a cube is really nice, because it's just like the bounds are all numbers. So let's cancel the centimeters cubed from these centimeters cubed, and then our final answer will just be in degrees Celsius. But the bounds are 0 to 1, 0 to 1, and 0 to 1. And you can do any order here because cubes are really nice. So I'll just do dx, dy, dz, because whatever. Okay, so we'll do the inner integral first, the integral dx. The outer integrals are just going to sit here and wait for us patiently. The integral of xy dx is half x squared y. The integral of 8z is 8xz. And the integral of 20 is 20x. The bounds are from 0 to 1. The 0 is pretty nice, so I'll just get to plug in 1. I get half y plus 8z plus 20. You should notice when you're doing a definite integral that each time you integrate a variable, the variable is gone. So like I plugged in 0 and 1 for x, so the x's are gone. Next up I'm doing a y integral, and then all the y's will be gone. Some people refer to this as integrating out the x's, and now I will integrate out the y's. The z's are going to be waiting for me. Integral of half y is a fourth y squared. Integral of 8z is 8yz. Integral of 20 is 20y. This is from y equals 0 to y equals 1. The outer z integral is still waiting, and I plug in 0 and 1 for y. So I get a fourth plus 8z plus 20. Now I can do the z integral. That's all that's left. So I get a fourth z, 4z squared, 20z from 0 to 1. And I get my final answer. It's a fourth plus 4 plus 20, which is 24.25 degrees Celsius. Notice that it's not just the average of the lowest temperature, 20, and the highest temperature, 29. Because of the way the temperature varied throughout the cube, more of it was at a lower temperature, so we got a little bit below 24.5. So that's a triple integral. My understanding of what will happen to you in physics when you have triple integrals is that most of the time the integrals are set up so that something good happens. When the integrals are not set up so that something good happens, there's a way to change your perspective, like switching to polar coordinates, that will make the integral come out to something good. But you will need to be able to like deal with all these variables and all these integrals, so you just have to practice a bunch of these and just try not to be afraid. I think you'll be fine.